It's the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 55, where today we are going to be talking about integrals. Integral calculus. I think this is a big one, yeah. We've been mentioning this for some time. You know, I think we had an episode on derivatives, so I think this had to come. This had to come sometime.
Mm-hmm. This was quite anticipated. We did do our episode called The Big Math, which I don't know why we called it that, but, you know, we meant to just say calculus.
Yeah,
and
that
we
summarized it.
Essentially, we just covered differential calculus, more or less, right? Like, we did limits, talked about rate of change, and obviously there is a whole other side to calculus, which is actually, like, it's not like an other side per se, because it's highly connected to differential calculus, but it's integral calculus, which is essentially differential calculus backwards.
It's literally called the antiderivative, right? So yes. I think that's also always like a nice way to think about it.
Because yeah. So when you just like going over it briefly, when you're doing a derivative, you're taking a derivative. Let's say you just have a single variable function, for example, x squared. You take a derivative, and then you get a new function that tells you the rate of change, the instantaneous rate of change at any point on your original function, right? But what happens when you have an operation that reverses that? So let's say you start with the function 2x, and you reverse differentiate, and you get x squared. What does that even signify, right? We're going to answer those questions in a little bit after we get over our little introduction segments.
Yeah, I think we have some... No, because the interesting thing about integral calculus is that a lot of people find it a lot harder than differential calculus, and
objectively,
it is. I mean, it's completely just, it simply is. But I think in a lot of like applications, and I say this especially because we're looking at integral calculus right now in our math courses, but the applications of integral calculus are like quite prominent in real world. Like, obviously, I'm not saying like, you know, like a construction worker is going to be using integral calculus in his day-to-day life. I'm saying like, obviously, for a person, this like integral calculus is important. The point I'm trying to make. It's
as important.
That's exactly what I was just trying to say. That like differential calculus, you know, can get understandings of maximums and, you know, local extremums and understanding how things are related in terms of like slopes and gradients and stuff. And then integral calculus, what we're going to get into, it like tells you something very different about the function itself, but still gives you a good understanding of, you know, the 2 variables, 3 variables, or whatever that you're dealing with. So it gives you a good idea of what's happening between the variables.
I was thinking maybe for our listeners who haven't taken calculus at all.
True.
Maybe we can go over just like real quick, actually, like derivatives and things like that. So essentially, like this is assuming you know what like x squared looks like, the graph of f of x equals x squared. For example, when you take the rate of change, the instantaneous rate of change at any point, it's like you're drawing a tangent line that is that represents the slope of that line represents your rate of change. And so if you actually take a derivative and you set the derivative equal to 0, you're going to find all the points where the tangent line to the graph is just horizontal, has a rate of change of 0. And why is that important, you might ask? Well, if your function is you know, curvy, goes up, down, you know, whatever. The points that are going to be the maximums and the minimums, sometimes global maximums, sometimes local maximums, will always have derivative 0, right? Because if you're increasing and then later on you're decreasing, at some point you will have an instantaneous moment where you are not increasing nor decreasing.
Completely 0, basically.
Yeah. And so that would be your maximum. And then the reverse, like if you're decreasing and then later you're increasing, there has to be a moment in between where you reach a minimum. And then by setting the derivative equal to 0, it's kind of like a hack, I'd say. Because before we actually took calculus, this was like a mystery to us, right? Like in our functions course, we had to graph functions, right?
Yeah.
But I remember I don't know how it worked for you, but in my school or in my math class, essentially all we had to do was find the roots of the function. Or if it was like a rational function, then we had to find like the asymptotes and all that. And then just draw it approximately, right? So if it was
I mean, before we knew any calculus, like that was the only thing that we could do because we couldn't like take derivatives yet.
But
so
it's interesting.
Yeah, of course.
It's interesting how like as a math student, they're like, okay, you find the intercepts and then you just kind of draw it however you feel.
Mm-hmm.
And then you get to the next semester where you learn calculus, and then there's like an actual procedure to fix those unknowns that we just ignored before.
And that procedure, in my opinion, is very satisfying. It's a very satisfying procedure because it always works. And, you know, like talking about like real life examples, like I definitely remember me mentioning this example in the big math. Like imagine like you have a profit function of a business. I just love this example with many variables, and you add them up in some fraction and some weighting, and they net to some total profit function. Like you would want to know the maximum of that profit function as a business owner or whatever. And that's just a mathematical fact that can be solved very, very simply using like differential calculus. So like that's where derivatives play a very big part in, you can kind of say real life, but yeah, you can use it for sure.
Yeah, and this topic might be a little bit advanced, but I think like with a little bit of visualization, it's very satisfying. How if your profit function depends on two variables, for example, let's say like the price of or let's say the amount of material you're using. For, let's say, the classic example is a box, right? Where like the lid is made out of a certain material and the walls are made out of a different material that all have different prices. And so your function is going to depend on
So in that case, you would try to minimize the cost.
Exactly.
So
it's now, when you're trying to find the minimum, right? I was talking about single variable functions. So all you have to do is you set the derivative equal to 0 and you find the minimum. But when you have two independent variables,
it becomes interesting,
right? And you output like this is, let's say, R2 to R. So you have two independent variables and then one dependent variable. You still want to know where the minimums and the maximums are, because that's obviously still a valid question. And so now we get into partial derivatives, which just have to do with the rate of change in certain directions. So for example, if I were to fix the value of y, then I can only look along x and say, what is the rate of change along x? Or, you know, if I take the partial derivative with respect to y, I fix x and then I just look along y. And the cool part about this is, I know maybe some of our listeners will obviously have seen this, the upside down triangle called nabla. That is, it's a differential operator. It's a vector essentially that you can do. Like you can apply it to a function, you can dot product it into a function, and you can also cross product it into a function.
It's basically an operator, so like yeah.
But that'll be, I think we'll definitely cover those.
Okay, also like I'm just imagining right now, like we've already totally gotten into the episode without like having any of our introductory segments. Like you even said after the introduction, and then we just got into it.
Okay, but one sec, I have to I was just gonna say, we're gonna talk about Actually, we'll make a follow-up episode on differential calculus in multivariable situations.
I mean, we kind of did cover some of that in the big math episode.
I don't think so.
We did talk about, because see, the interesting thing about multivariable calculus is that now in this profit function with like two variables, you have to look at, well, remember in the one single variable case, we were looking at, when is this derivative 0? So in the two variable case, you have to look at, well, when are both derivatives 0? But, well, with multivariable calculus, there are a lot of these interesting caveats that can occur where one of them is a maximum and one of them is a minimum. And that technically isn't a maximum or a minimum of the function. So there are a lot of these interesting things that happen when we add one more dimension.
We can definitely make an entire episode just talking about gradients, talking about curl, divergence, Lagrange multipliers, critical points. What are those called? The forms. What are those called? Like the indefinite form.
Oh, indefinite, positive, definite.
What is that called? Critical
quadratic
forms?
form?
Yeah, quadratic form.
The quadratic form.
We can also
That's
talk
an interesting
about
thing to get into, but like it does require a little bit of history,
Yeah,
so,
that's true.
Before we get into it, because I'm actually very excited to get into it, because we already kind of did get into the episode, but I do want to officially get into the episode. But before that, the introduction. So, for the segment of the week, we have the comment of the week. Parker said we mentioned her before, and I think we did as well, but I'm not entirely sure. I kind of forgot. But we have Shreya here with the comment of the week, where she says, I follow you guys on Spotify, Instagram, and subscribed on YouTube with notifications on everywhere. Yes, I'm obsessed. So I was just kind of giving the same energy that I'm assuming she was writing this with. So thank you, Shreya. Thank you, Shreya, so for this wonderful comment.
Make sure to leave a comment under this episode to get featured as the comment of the week in the following week's episode. And also to follow us on Spotify, Apple, YouTube, Instagram, wherever it is you are essentially.
So, definitely check out our YouTube though. Like I think our YouTube, it's not obviously like our Spotify, like our audio is like one whole section of the podcast, but like, like right now, especially like we're putting a considerable amount of effort into the YouTube videos, like into like the thumbnails, the clips and stuff like that. I really think the clips are really cool. So like, just check it out if you guys want. And if you guys are following us on Instagram, then you probably already know all the stream of clips that always come out, because all of the YouTube ones go on Instagram too.
For sure.
So so just check us out anywhere. But
also, we are very, very close, essentially already there at 90,000 downloads. 90,000.
That's amazing.
That is
insane.
incredible.
We just got 10,000 more. 10,000 more for the big 100.
That's right.
That's pretty insane. That's pretty insane.
On YouTube, 450 subscribers. Thank you so much.
Nice.
To our YouTube viewers.
We're getting there.
And 6,750 Spotify followers. Thank you so much.
Insane.
Keep on listening.
Yeah.
And watching.
Tune in. Keep tuning in.
Okay, we can get into this integral calculus. And so first thing that we learned before going into integration was actually infimums and supremums. AKA
classic.
Extrema. Or actually, no, extrema is minimums and max.
Yeah, extrema is minimum and maximum. These are not extrema. These are just What are these? Are these like a? I think it's just because it's like a property of any set. Like a set will have a supremum, will have an infimum.
Yeah, and
I don't know what they're really called.
Just to be explicit, the infimum is the highest lower bound, and the supremum is the lowest upper bound. Okay, so
that would be so confusing if I just heard that for the first time.
Yeah, but here's an example. Okay, so if you have an interval, let's say this is an open interval, so the endpoints aren't included, right? And then if you're like any number that comes before the interval starting is a lower bound, because you can say that, okay, let's say my interval is 0 to 1, not including endpoints. I can say, okay, -2 is below every single element in that interval, so it bounds the interval from below. But there's actually only one number that is the highest lower bound, and that is 0, because 0 is less than every element in the set, and even if you go a tiny infinitesimal step higher than 0, it is no longer going to be an infimum. That's just how like the open interval kind of like a characteristic of it, right?
And the same thing on the other side, right? Like when you're talking about the supremum, like that's basically like the upper bound of that open interval, basically bounds it from the top, and describing it as the least upper bound, right? Like the smallest possible upper bound of that set, taking in all numbers taking into consideration. So we have these two definitions, supremum and now infimum, that tell us some interesting things about integrals. Well, actually, it doesn't, not quite there yet. We kind of also have to get into like rectangular areas.
Partition,
like,
actually. But I don't think we're going to talk about the multivariable case today, because there's
maybe
too
not.
much. There's too much ground
maybe we won't
to
get
cover.
enough time, but maybe we can like touch on it, because there are like some really useful applications of multivariable integrals.
Yeah.
And I think, in my opinion, the applications of the integral actually become useful in multivariable calculus. Because in single variable calculus, you're like, okay, I can get this area, but only for like mathematical reasonings. You know, like it's very important in statistics, for example. Like if you guys, you know, like in a probability function, you're always integrating things. So it's very important. But in like real life, for like surface area, volumes of like crazy, like manifolds, oh, I shouldn't use that word, but crazy surfaces, like all those kind of things can be solved using multivariable integrals. So maybe we won't get into it, but it's an interesting thing to, I think, like, you know, just
I think
touch.
you mean like surface area, because
yeah,
you
like
just said
area. That's what
you said surfaces can be solved using integrals, but like
no, like surface area. Oh yeah, sorry, I meant surface area can also, obviously, like surface area, volume, all that stuff in higher and higher dimensions can be solved using multivariable integrals.
So this will actually make sense in about 5 minutes, but I do have to mention what partitions are, okay?
Okay, let's hear it.
So we're just going to work with intervals, right? You have an interval. Let's always take the classic 0 to 1, okay? And a partition, right? I believe I believe a partition is a set of points. It's a set of points, right? That are all contained inside your interval, and it has to contain the endpoints of your interval, or no, technically the supremum and infimum, because the endpoints might not be contained. But anyways,
that's right. Because that's right.
I think that's
because
right.
if it's an open interval at like 1, then 1 won't be. Yeah, you're right. You're right.
So it has to contain the supremum, the infimum, and then there's the trivial partition, which is actually just the supremum and the infimum, which just separates your interval into the interval itself. But usually we're interested in nicer, more useful partitions, and it's just a set of points that you can separate your interval in. So let's say there's 1 point at 0.5, then you partitioned your interval into 2 segments. Boom. There you go.
So basically, I think we are getting really ahead of ourselves without actually explaining really anything about what the integral actually really is. So like, again, the reasoning behind all of this, like why we're partitioning all this stuff, is because what the integral represents is, in differentiation, we have the slope of the curve or of the graph. Let's say we're talking about a single variable. We're talking about the slope of the curve.
Yeah, this might have been useful to mention earlier.
Sorry?
This might have been useful to mention earlier.
Right. I mean that's what I'm mentioning it now. So at least like a quick recap. Integrals, on the other hand, represent an area under a certain interval. A weighted area. That's a good way to put it. Because in derivatives, you can find a derivative, and you're supposed to find a derivative at certain points on the curve. But in integrals, an integral under 1 point makes zero sense because you have to find the area of an actual interval. Now, here's the problem. What happens when the curve is all weird? Like the same example with if we have a straight line with like a linear equation, to take a derivative is very easy because it's the equation of the line. Y equals mx plus b. What's the derivative? M. Like it's the equation of the line. But when we get to x squared, x cubed, x to the 4, we have to start using these things called derivatives. So similarly, when we have more complicated things than constant functions and simply lines, where we can just, take the area manually of like a trapezoid or a triangle or just a rectangle, because that's very easy. What happens when we have like a weird curve, right? And that is where the process of integration becomes useful. And the reason for us partitioning this interval is because sometimes there can be some really weird things that the curve does in that interval. It can go up, down, sideways, left, right, and then it could end up at the end point. Basically, it can do anything is the point that I'm trying to make.
Wait, are you talking about the graph?
Yeah. So like what I'm trying to say is the graph can, like, the between the endpoints, it can do whatever it wants. So the reason of us taking these partitions is so that ultimately we can take almost infinite partitions such that we can get very... Sorry?
The name of the game is chopping.
Yeah, I mean, that's what I'm saying. We're trying to chop it into infinitesimal widths.
I think there's these
infinitesimal rectangles.
There's an important visual that it has to be mentioned. It's that if you have the area under a graph, if you chop up the interval underneath the graph, and then what you do is you just pick a point that is pick a point inside that interval, and then you have f of that point, so the height of that point multiplied by the width of your partition, and that is going to give you an area. But the thing is that it's going to be very off from the actual area.
Obviously, depending on the curve, though. Yeah. It depends on the curve. If it's just
it might actually be
exactly. I mean, if it's a flat curve, if it's constant, it would be the area. That's right. Yeah. But if it's going haywire around that point, there can be various things, right?
So the name of the game right now is to make the partitions finer and finer. And so your rectangles get thinner and thinner, but obviously you'll have more rectangles. And then you take the limit, which we talked about limits in our previous episode. You take the limit as essentially the length or the width of your little partitions goes to 0. And then suddenly you have a very smooth, infinitely, it's rough, but it's infinitely not rough, if that makes sense. And then you get a really good, it's a really good approximation, but in the limit, it becomes equal to the actual area. And the reason why I said weighted area earlier is because obviously in the real world, area is positive. You can't have negative area. In the integral world, if the area under the curve is above the graph, or above the x-axis under the graph, it's going to be positive area. But if the function goes negative under the x-axis, that area is going to count as negative area, which doesn't really make sense, but that's just how it works. And also, you can actually calculate the if you want to actually find a positive value for the area under the curve, that's doable, right? Because you just take the absolute value of your function, and then you find the area.
But that's also mainly in real world examples. But also even in real world examples, you can still have the curve going underneath the graph, as long as I guess the net area still remains positive, which has happened in when you're dealing with motion of cars and stuff in grade 11, and you're taking the area under these boxed graphs and stuff, and you're saying, oh, the net area is still positive, so we're good. So it still depends on the net idea. But again, like that understanding of the integral is quite fundamental, because like you understand that taking these infinitesimal changes can, react to a better understanding. And obviously, as that infinitesimal change almost goes to zero, again hinting at the limit, we get that perfect smooth curve as you were describing. And interestingly enough, and can't have mentioned this more, I keep mentioning this any chance I get, integrals were invented before derivatives. Or at least that's how Newton did it. So Newton actually invented integrals when he was, I believe he was trying to kind of analyze the motion of a falling object. And he took the area, or he devised a way to calculate the total area under a projectile's graph, I guess. And that was, I guess, the first use of calculus, or integral calculus. And this guy was just quarantining at home.
That's pretty impressive.
Just make integral calculus, But
Not
anyway,
bad. If you do want to learn more about Newton, we have a history of physics episode on Newton / Richard Feynman, I think.
Yes. Yeah, that was our first history of physics episode. That was really cool. That was a really cool episode.
History of physics coming soon, though. Episode 3 coming soon.
You know why? And we should definitely mention this. If you follow us on Instagram, try to come to our IGTV, I keep saying IGTV, like our Instagram live sessions. Like we have these Instagram lives sometimes, and like people recommend episodes on there, and like because we're live talking to them, like we're talking to the audience, like we're talking to you guys, obviously, because it's an Instagram live kind of situation. So like you guys give us some good feedback and you guys give us some good ideas, and we're like, okay, maybe we'll do that next episode kind of thing. So someone recommended it in the Instagram live, and we are doing their recommendation. So I guess we're not going to spoil the names on this episode, but
no, it will
Instagram
remain a surprise.
It is a surprise.
Next up, we're talking about integrals, and the fundamental theorem of calculus actually relates differential calculus and integral calculus all together in one package. And there are actually two fundamental theorems. I think we'll only talk about one of them because the other one is more like useful for computations, which podcasts, so we're not going to do that.
Not going to get into that.
But one of the versions, or one of the parts of the fundamental theorem of calculus is that the integral of the derivative of a function is equal to the function itself. What does that tell us? Okay. Well, this tells us that if you take a function, differentiate it, and integrate it, you get the same function back. And so why is this important? This tells us a lot about how to compute an integral, right? Let's say we have the integral of a function, and you want to say, okay, equals to, well, what? Okay. As soon as you look at the function that's inside, it's called the integrand. As soon as you look at the integrand, you need to think of that integrand as the derivative of some other function. Because if you can figure out what that other function is, then boom, that's your answer, right?
Also, though, plus C.
Yeah, but
I forgot about the plus C.
But there's no plus C in.
Well, there is a plus C. Not
in that part of the fundamental.
Because there? I'm just thinking about this.
Oh yeah, there
X
is.
Squared. You differentiate
right.
it. 2x. You integrate it.
You're right.
X squared plus C, right? It would have a plus C.
Yeah, you're right.
So there would be a plus C component. So I guess there's some, because again, this plus C, if you already have some value that you're evaluating this at or something, like it would simply be that initial starting point. But if you don't have anything, this still gives you a very good idea of what the function actually is that you're trying to solve for. And that's what's important, because you're trying to solve for f of x here.
So I'll actually
or whatever the function is.
I'll actually explain what the plus C is, because Rayal just said plus
I guess
C.
I didn't even oh yeah, sorry, go ahead.
So,
maybe you want to do that.
This is actually something that first year calculus students forget all the time. And it's that when you find the antiderivative of a function, the most general form is actually like plus a constant. And this is actually pretty interesting when you think about it, and I will help you think about it right now. So when you take the derivative of a function, okay, we all know that the rate of change of a constant is 0, right? So if I take the derivative of x plus 2, the rate of change is going to be 1. And if I take the derivative of x plus 1,000,000, the rate of change is still going to be 1. Okay, which means if you give me the derivative of a function and you say integrate this function, or give me the antiderivative, the thing is there is not one single antiderivative for one derivative. It's actually a family of functions which can differ by a constant. Okay, so for example, if you tell me, okay, what is the antiderivative of 1, which is the example I just gave you, I can't just say it's x, right? Because if you differentiate x, you get 1. That is true. But as I just said, if you do x plus any other constant, it will give you the same derivative. So that is why we put plus c, because the antiderivative of 1 is x plus any other constant. And this is obviously true in the general case for any function you pick. The antiderivative is just a family of functions that all differ by a constant. So the general case, you will have to just do plus a constant c.
Mm-hmm. And these integrals are like, these families of functions is kind of interesting, because when you integrate, you get this family, but when you differentiate, you get this one number. And it's also important to note to note that this is like the indefinite integral, because like because we were talking about integration like it represents something. So when we're talking about integration, like integrating from some interval, like some open to open or something like that, any interval basically, we're talking about a physical meaning. We're talking about the area under this graph, if that's what we're doing. Right? Yeah, so like we're talking about something physical. But when we're talking about the indefinite integral, we're no longer necessarily talking about something physical. We're now talking about something a lot more mathematical. Like we have some curve, and if we want to know the area under any possible interval, we get this indefinite version that we can just plug in values into, right? So we basically have this idea of indefinite integral where it returns a function, which is kind of different from our original notion of what the integral is, which is an area under a curve, which represents the area and not necessarily just the function. So it's an interesting.
And so some of the integration rules are very easy. Others are very hard. Mm-hmm. Some are just impossible to do. Well, I should be more specific. They're not literally impossible to find like an answer for the antiderivative, but with like easy integration like tips and tricks, you can't solve it. For example, the Gaussian integral. You can't just do like a substitution or do an integration by parts. None of that works. You actually have to do, isn't it? You have to do like a infinite sum, right?
With the Gaussian integral, yeah. I believe it was a Wikipedia page that I looked at. Well, and I do not remember it.
Well, here's the thing. I actually know of one really clever way, which I might give like 2 minutes to explain. If you actually call like the Gaussian integral I, and then what you do is you multiply it by itself, but you use a different integration like variable of integration. So now your first integral is with x, and just for the listeners, the Gaussian integral is the integral from minus infinity to infinity of e to minus x squared dx. And essentially what you do is you have your first Gaussian with respect to x, your second Gaussian with respect to y, but because we know that these converge, this is just equal to the integral squared, because you just multiply it by itself.
You do know that there's so many things that you just said.
I'm explaining it to you. Like,
okay, you're explaining it to me. Okay. Well,
are you understanding?
Okay.
So
I don't
now
know why
you
you're
have
explaining this to me,
X
but
and
okay.
Y. But
Okay. Yeah.
as you know, as we learned, Fubini's theorem. Right?
Oh.
Now you can turn this into a multivariable integral, switch to polar coordinates, and you can actually solve it. And it gives you. I mean, obviously, it gives you the right answer. But all I'm saying is that that's one way to solve it. I don't.
Yo, what just happened? It went from talking about integrals
but at least tell me
double
you're
integrals, then
understanding what I'm
Fubini's
saying.
theorem, then switch them, then polar coordinates, and then computation.
But at least tell me you understand.
No, obviously, yeah, no, I understand that method. Yeah, we did it in class. It's a really cool method and way to solve the Gaussian integral simply by switching the order of operation, like the order of integration.
But we did a different example.
Yeah, I mean, we did something very similar, but like I understand the idea that you're following is very similar in the sense that we basically swap the integrals. And again, this is more multivariable integral, something we very specifically said we would.
No, but this is just especially interesting because you're solving a single variable integral that cannot be solved. Like
that is an interesting point to pull out of that, though, for sure. That you can't do it with one integral. You would need a multivariable situation.
Yeah, so you turn it into a multivariable, which is much easier. Unintuitively easier to solve. Yeah, something like that. Anyways, here's the kicker, though. Here's the kicker. I know everybody in the chat right now. We're not live. But I'm saying, as in the metaphorical chat right now, wants to know more about integration. Wants to know more.
They do.
About the beautiful world of calculus. But where do you go to actually learn and put your skills to practice on the spot? That's brilliant, ladies and gentlemen. Brilliant.org/MPP. They have incredible math courses. What can I say? What more can I say, right? They have, especially today we're talking about integral calculus. They have a course where if you know nothing about math or you don't remember anything about math, you can even start from the basics, the math fundamentals, work your way up to algebra, pre-calc, or functions, pre-calc, and integral calculus, multivariable calculus. It's all there. It's all there. And it's amazing. The tools are great. The interactive activities, they really help you just take in the content and hammer the ideas into your head.
Again, a big reason we endorse it is because it's also so good. And it's kind of what we keep telling people, the one thing, especially with math, I guess physics, this also does apply, but especially with math, practice. And sure. that's one of Brilliant's big mottos, especially with the math section. They have so many practice routines where you basically kind of force your brain to learn it in a way that's kind of satisfying, that leaves you satisfied at least. So it's really nice because again, Parker and I have used some of the courses. So it's a really interesting thing to see the way they do it versus, different platforms. So definitely go check it out. The first 200 people to sign up with a link in the description below, which is brilliant.org/MPP, or as I said, in the description below. First 200 people get 20% off. Take that. Dang. 20% off their premium membership. Off? That's pretty amazing. So go smash that link. And go check it out. You can just go check it out. See if you like it. And
the best part, I think, this is kind of like dragging on the ad, but it's okay because it's interesting. The best part is that there's no like pressure of like exams, quizzes. You just learn when you're interested. You know what I mean? And I think that, like, for us, obviously, we have exams and quizzes, but we just do it because we learn a lot in the process. But obviously, if that's not your career, you're just interested, you can still learn the things that are in the field, right? You can still see how interesting math and physics really is. And yeah, of course, resources are all over the internet. And Brilliant is just a great one.
Mm-hmm.
But returning to our main topic of the evening, I guess we can get into multivariable.
I knew it. I wanted that. I wanted that moment. So here we have us dipping our toe into the multivariable integral. But before that though, I did think about something that maybe we can talk about, because I mentioned it and I just think it's important because it does have something to do with integrals. And it's also, I guess, a little important. I was just thinking about this mainly because I guess
say
I just
it
mentioned
already.
it. I'm just gonna say it.
Oh my god!
The probability density function. Oops, my mic just. Well, that was weird. Sorry. The probability density function. So the probability density function, which can be a single variable or a multivariable function, is basically a function that takes in a bunch of parameters, and it tells you the probability of certain combinations of those parameters. So if, let's say, like you had 2 coins and you're like, what's the probability I get 1 head? It'll map to some point. I have 10 coins. What's the probability I get 3 heads, 7 tails? It'll map to another point. So this probability density, I mean, obviously this is a very simple example, a discrete example, because they're discrete values and it's not continuous. Very simple example, but obviously, as I said, it can get a lot more complicated. So the idea is you have these variables and you have this function that represents the probability. Now, why is it so important? And what does it have to do with integrals? Because a very important property of probability density functions, and again, this appears a lot in statistics, and I'm in statistics, and Parker always hates that. Parker always hates that.
This guy's a nerd.
For some reason. I don't know why you hate statistics. It's amazing. But anyway, so it comes up a lot in statistics, and it also comes up a lot in quantum mechanics, right? So a very interesting thing about the probability density function is that the total area is 1, which makes sense, because the sum of all possible probabilities should be 1, right? Like this is 20%, 30%, 40%. Like they should all add up to 100%, which is 1. So that kind of makes intuitive sense. But what does that mean? That area is basically the integral, right? So if I want to know probabilities of certain events happening, I would have to integrate over certain variables.
And now we've actually seen recently, and also not so recently, applications of this probability density function. For example, in quantum mechanics, obviously, there's for example, the position probability density. You're asking the question, what is the probability that your electron is sitting between these 2 distances from the nucleus, for example. And an interesting thing about that is you realize that the probability for an electron to be at 1 distance is 0, because you're integrating over 1 single point, right? And the area under a single point is obviously 0.
I mean, it's not 0. It just doesn't make any sense. It's not exactly.
It is 0. It is 0.
Is it 0 or no? Because I thought that it's just undefined.
This is actually the fundamental theorem part 2 that we skipped. Is that if you do have a definite integral that's being integrated between 2 bounds, you just plug in the 2 bounds, you do final minus initial of that antiderivative. And so if you're integrating over a single point, you're integrating, let's say, from 0 to 0. So it's
just f of something minus.
You're going to just plug in f of 0 minus f of 0.
Okay, I guess I didn't think about it. Yeah,
and so the answer is actually just 0.
You're right. I guess that's the way. Yeah.
Another application is that we saw this in thermodynamics while talking about Maxwell speed distribution of, for example, particles in an ideal gas. It's this like bell curve kind of shape that you get. And yeah, that's interesting also in the same way, because the probability that you find an oxygen particle moving at a single speed is 0. You have to be looking at intervals of speeds. You can actually like get very small with your interval if you want to be quite specific, but obviously should we talk about uncertainty or
I don't know if we need to get into uncertainty because that doesn't have I mean
no, that's
not necessarily.
Fine.
I think that would be going the extra mile. But I did want to add something like when you were talking about like probability and quantum mechanics, because like, and I think we have spoken about this before, one of the most fundamental things in quantum mechanics, like mathematical features about quantum mechanics, is the wave function, right? The quantum wave function, which basically describes the state of all the particles in a particular system. And by itself, it means squat. It means absolutely nothing. But when you square this guy, you get the probability density distribution. And again, that is again where integrals become very, very helpful. If you're trying to find the probability of certain events, of certain states, of this particle, of this system to be in certain states, to be in mixtures of certain states, all of this rises from integral calculus, and it assists a lot of the math behind quantum mechanics. So it's really interesting to see where it can be used.
Like one thing that's definitely nice is that when you start doing multivariable calculus, you start seeing it right away in your physics courses. You start talking about electric fields, which is all, gradient, flux, surface integrals and all that. You also see it in classical mechanics and obviously quantum mechanics, where you have to start like integrating over these probability distributions. And it's awesome, obviously, because you unlock this like door in physics that you couldn't really talk about before. Imagine your professor starts talking about surface integrals and you're there. I mean, actually, that is actually what happened to us in first year.
What?
When we were doing electric fields, like Gauss's law and things like that. And then our professor
brought up surface integrals. I remember.
Well, yeah,
when
he was talking about surface integrals around like the point charge and all that stuff.
Oh, I remember.
But he did tell us, like, I remember actually one time, this was like after the lecture, I went up to like the front and I asked him, I'm like, what's that like squiggly line with the circle through it? And he's like, oh, that's actually like a closed integral over the surface. I'm like, oh, I have no
That's
clue.
Interesting.
I have no clue what those words mean, but thank you. But he did say like, okay, just don't even worry about that.
At that time, we simply needed to know what that integral equaled. Like we didn't really know how that integral worked.
Yeah, we actually.
But now look at where we are. We're big boys now.
The reason why we actually were able to just ignore the surface integral aspect is because in first year electrostatics or whatever, you only deal with like highly symmetrical problems, which means that the surface, or in like most cases when you're going to use Gauss's law, the electric field about like your surface is going to be the same at that. For example, if you have a point charge and a Gaussian sphere, the electric field is going to be the same at like a distance r all around the charge. And so you can literally factor that out of the integral and just multiply it by the surface area. But obviously, second year and beyond, you start seeing not so symmetrical things where you actually have to do the surface integral and etc.
There's some, I mean, as we're bringing it up, some very useful aspects of these integrals. And are we trying to get into multivariable or just a little bit of the added dimension?
I don't know, to be like, I feel like this would be better if we did a whole episode. If we did a whole episode on like first we talk about like visualizing like graphs from R2 to R, like what the graph would look like, also vector fields, also things like, well, now we already talked about integrals, so we can talk about line integrals, things like
No,
that.
because in higher dimensions, like there are a lot of properties of integrals that, you know, can be discussed, and very like interesting things, you know, with the with the parametrizations, for example, of certain boundaries. You can integrate like a whole very complicated surface and stuff like that. Like, anyways, that might have been very complicated words to someone who hasn't heard those set of words before, but like there's some really cool things that we can do with multivariable integrals.
I think we can even just talk about multivariable like setups, essentially. Like we can talk about like just parametrizations on their own, and talk about shapes.
I think the first thing we should talk about, and I don't know why, I just think this is important, but it's also, and we can talk about its disadvantages, is something called the Jordan measure. Right? Now, the Jordan measure is a very important metric to classify if a certain surface, a certain curve, a certain whatever you're trying to integrate in the scenario is integrable, right? Because there can be surfaces that are non-Jordan measurable, right? Now, that again might make no sense because I haven't explained what Jordan measurable means. But there can be some surfaces that just cannot be measured. And you know what? Let me just explain what it is, because I just repeated myself without explaining it whatsoever. So let me explain what Jordan measure is. In the simplest way possible, it's basically asking you, can I find the volume of the surface? That's basically what it's asking.
Volume, of course, is being generalized to length, area, and volume, and 4-dimensional and beyond.
Depends on the dimension. When I say volume, exactly. So if we're dealing with 2 dimensions, I mean area. If we're dealing with 3, I mean volume. If we're dealing with more, I don't know what it's called, but it's basically just multiplying all of their components. So I'm basically talking about that net. Again, I can't say volume, but like that net thing.
Oh yeah, that's what it's called though.
Volume. I mean, technically it is called volume, even in higher dimensions. So I guess we can just generalize it to volume. But yeah, so the idea of Jordan measurability is to classify, hey, is this set integrable or not? So that means, can I measure?
Measurable.
Sorry?
Not integrable. Measurable.
Measurable, yeah. So is this set measurable or not? It's basically a question of, but that will tell us if it's measurable or not. The fact or the state of its integrability. Can the surface be integrable? Will be determined.
That doesn't make sense.
If it's measured.
No, functions are integrable, not surfaces.
Well, I guess, okay, I mean like the function on the surface is what I'm trying to say, because there's a certain surface, and if it's simply not Jordan measurable, you cannot integrate over that surface. Obviously, you're not integrating the surface itself. I mean like function along the surface. You're having a quick thought.
No, I feel like that's not true. I feel like they're this might be totally wrong, but I think I remember our instructor saying that even if a set is not Jordan measurable, doesn't mean you can't integrate over it. Yeah, actually that is true. That is 100% true. And let me give you a counterexample. If you have the set, it's I'm sure you'll remember it. We talked about like some intersection with the rational numbers. Like it was some rectangle being intersection with the rational numbers, and the function was the actual example is eluding me. Is that a word?
Wow, you just came closer to your mic and your audio sounds so much better.
Loud?
No. It's better. It's better. Your audio's better.
Oh, sorry.
Like I just noticed because you were sitting back the whole time and you just came in front. It sounds so much better now.
Okay, well that sucks. But yeah, I will try to find it and let you know. If
I'm also actually trying to actively find it right now, because see, let me explain. If a set is Jordan measurable, then its indicator function is integrable which would mean that the function can be integrated over that set.
That is not true, because a function can be non-integrable regardless of the set. The set doesn't say anything about the integrability of the function.
Then what am I talking about? Wait,
I don't know. I don't know what you're talking about.
No, because I'm talking about... Because there are certain surfaces that have... Like when you're talking about the Jordan measurability of a set, right? So if I say a set is Jordan measurable, what does that help me with integrability?
To be honest, I'm just like... Not even I'm like, because right now my brain is focused on like the modules we're on right now, so I don't remember. But,
yeah, this is a module that we did a few months ago, but again, we should know this, man. We should know this.
Whatever.
Like I'm just thinking.
To be honest, it is what it is.
Okay, so listen to this. So I think I was right. If S is Jordan measurable, and the set of discontinuities of F on S has 0 Jordan measure, and I'm going to explain that in a second. Don't go anywhere. Then F is integrable on S. So, for a function to be integrable on a surface...
Hold on. That doesn't mean that if S is not Jordan measurable, F is not integrable, because it's not...
No, F is not integrable over that set.
No, but that doesn't... Like, you know, you're saying if S is Jordan measurable, blah, 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 then F is integrable. But that doesn't say anything about the other way around.
No, like, I know that. I know the direction of the if then.
I know, but you were saying that if S is not Jordan measurable, then you can't integrate the function.
So what you're saying is we can integrate a function on a non-Jordan measurable set?
I think there is a counterexample.
You think there is?
I think there is, yeah. It has to do with upper and lower sums.
To my understanding, and again, we did do this a few months ago, but this shouldn't be an excuse because we just did it a few months ago.
How did we not even talk about upper and lower sums in the
podcast?
We
went this whole podcast without talking about upper and lower sums. We spoke about infimums and supremums.
Yeah.
But we didn't talk about upper and lower sums.
No, I remember why. It's because I was going to talk about partitions and then you cut me off and then started talking about what the actual integral was. Oops. And then we never got back to it. Okay. Anyways, we can always like make another episode or whatever.
Yeah, so I guess it's not okay. So again, we're just simply trying to find the set where it simply states that example.
Yeah.
Where a set is not Jordan measurable, but you can integrate a function on it. So
I think
it might exist.
I think we have gone off the rails now.
Yes, we have gone very much off the rails. So again, I did mention something that I did say I would come back to when I said 0 Jordan measure. And I said, I will explain it. Don't worry. Don't go anywhere. Okay. So 0 Jordan measure.
I think we'll end the podcast after that.
Okay. Maybe. Because again, we have gone a little bit off topic. But it's interesting because we're talking about multivariable in this case. So it's a very interesting notion. So 0 Jordan measure.
There's a lot of things that we didn't talk about, which kind of bothers me because we're just talking about like Jordan measure for no reason, you know?
No, but I think Jordan measure would be important simply to understand like the sets that we can integrate over in 2 and 3 and 4 dimensions. Because in higher dimensions, because in a single variable case, you simply have x and y and you can draw out a function and boom, you can integrate over this interval. But in 3 and 4 and 5 dimensions, that's not necessarily the case. There are certain surfaces over which you simply cannot integrate. So I just thought that since we're talking a little bit about multivariable calculus,
but that's also true
maybe I introduce these surfaces.
That's also true in one dimension, because you don't just need it. You don't just have intervals, right? You can have like a set of.
You can have a set of points, but I think you can agree that the set of points get a lot more complicated when you talk about higher dimensions.
Well, it does. Yeah. But my issue is that we're gonna talk about like 0 Jordan measure, and then it's like, okay, what now? We have another like hour of stuff to cover for that to be like useful.
I guess that's so okay. I guess we don't have to necessarily complete this Jordan measure talk, but we will be talking about it.
You could finish like.
No, but I'm saying if we're anyways going to have like a multivariable calculus episode, then maybe we can just talk about it there because it would be more apt on an episode of that caliber. So maybe we don't have to talk about that here, because we did talk about single variable to a very good extent, I think. We spoke about, where it's useful in real life, like what it means to integrate a function, indefinite, definite integrals. We spoke about, how integrals work, partitions, rectangles,
for sure,
infimums. I think we covered good ground today on integrals.
So yeah, if you enjoyed this episode on integration,
for sure,
go and follow if you're not following the podcast already, and also come watch us on YouTube, because we are here, we are live, not live, but in person. You can see our faces on YouTube.
Yep.
Follow us on Instagram, also TikTok, maybe.
Okay. So think about TikTok. Quick news about TikTok, right? So like, we mentioned a few episodes ago, and this is like a good 10 episodes ago, maybe. No, maybe less. No, less than 10 for sure. Where we're gonna continue doing TikToks, and then we never continued to do any TikToks. But I'm not gonna make any promises. But I'm gonna say maybe we're gonna have some TikToks coming out.
Okay, great.
Maybe. But like, it's good because now we actually have a good idea of what we're looking for in the TikToks. Like, we're only looking for 2 TikToks a week, like 3 parts, like per clip kind of situation. Sure. And then like, if you guys like that, you guys can view the full clip on YouTube or Instagram or whatever.
Sure.
So like, that's the whole idea of it. So let's see how that works.
All right. So, this has been episode number 55 of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we will see you soon.
Bye, guys.